Hello everyone, I would like to give my presentation about our research obtaining hard real-time performance with rich linear features in a compound real-time operating system by partitioning hypervisor. I'm Yang from Software Laboratory, University of Tsukuba, Japan. First is the background of our research. It's about real-time operating systems, RTOS. Real-time operating systems are used to support various critical applications, and it provides a dynamic execution environment. With the development of IoT and edge computing applications, real-time applications are now demanding more and more features from the operating system. For example, graphical user interface or rich networking. This inspires approaches to transform existing general-purpose operating systems GPOS into an RTOS. A popular candidate nowadays is Nuttx. Taking Linux as an example, there are multiple real-time Linux implementations, but most of them have their weaknesses. In addition, they modify the Linux kernel itself, therefore the Linux kernel cannot be used as is. Two representative approaches include modifying the Linux itself or adding a kernel design. Examples of solutions based on modifying the Linux kernel itself include SpringRT, RT-Linux, and Linux Arcade. These solutions tend to preserve their compatibility to Linux, including both API and application binary interface API compatibility, so you can reuse Linux binaries. However, most of them don't have a strong real-time guarantee. On the other hand is the co-kernel design. This includes the L4-based solutions and Xenomide, similarly RTAI. They deliver hard real-time performance but having weaknesses of lacking full support with Linux API, therefore programming and accessing Linux features are very difficult. It is not always possible to use the Linux binaries because of not fully compatible with Linux. To counter these weaknesses in existing solutions, we propose a new real-time operating system design. It's a compound RTOS supporting the concept of rich real-time application, which I will introduce later. It has the hard real-time performance by having a short bounded jitter, and it works without patching the general-purpose operating system to achieve good maintainability. It allows access to the feature of general-purpose operating system, presenting a good usability. We used Hypervisor to run two different kernels, a traditional RTOS, Swift RTOS kernel, and a general-purpose operating system kernel. We do not modify the kernel of the general-purpose operating system, making this compound RTOS easy to involve with the original general-purpose operating system. The overview of our proposed system is like this. In our compound RTOS, there are two virtual machines running on the same machine with a hypervisor. The hypervisor creates a strong isolation between the two virtual machines to improvise the real-time performance. Each virtual machine has its dedicated hardware resources, and the non-real-time devices are assigned to the first virtual machine, and real-time devices assigned to the second virtual machine. These two virtual machines create two ReLAMs. One is normal ReLAM, another is real-time ReLAM. The normal ReLAM runs the general-purpose operating system, and it can access the non-real-time devices and provides rich features. On the other hand, the real-time ReLAM runs a Swift RTOS kernel for accessing the real-time devices and executing the real-time applications. These two ReLAMs are interconnected by a shared memory. A rich real-time process executed in the real-time ReLAM by Swift RTOS but has access to the normal ReLAM's general-purpose operating system features. It has two kinds of threads, a real-time thread and a non-real-time thread. The real-time threads are responsible for executing real-time algorithms, interacting with real-time devices via real-time system calls. The non-real-time threads are used for interacting with normal ReLAM's general-purpose operating system and accessing its features via remote system calls. The developer creates a process with these two kinds of threads and manages synchronize them using the standard process threading APIs. In our implementation, we use Jailhouse Hypervisor because of real-time performance. It's a partitioning hypervisor without sharing hardware resources or virtual CPU scheduling. This might lower the hardware utilization rate, but improves the real-time performance. Variant Linux is a ready-for-use case for Jailhouse, therefore you use Variant Linux as a general-purpose operating system without modification, but only kernel modules. For Swift RTOS in our compound RTOS, we use Nuttx. Nuttx is a small open-source RTOS for embedded systems with real-time scheduling, real-time handling of interrupts, and process-compatible interfaces, including system calls, to files, and signals. Because Nuttx and Linux are both conforming to POSIX, this minimizes our modification to the Swift RTOS kernel. To be compatible with the x86-64 Linux we used, we ported Nuttx to the x86-64 with the same processor hardware setting. Nuttx consists of architecture-dependent and independent parts. During the implementation, we only add new code to the architecture-dependent part. For the normal rhythm, to execute rich real-time applications, we propose a mechanism similar to a remote asset call. It is able to load both dynamic and static linear EDF binaries to the real-time rhythm. This enables the use of existing binaries toolchains during the development of applications. For the real-time rhythm, executing rich real-time applications, traditional fork and exec pattern of units can be used. To support this, we solve the following problems and implement them as a Linux compatibility layer in the Swift RTOS. First is that we implement a separate and Linux-compatible address space for each process, and we also implement a full API compatibility with Linux, and furthermore, we also added system calls which are essential for the GNU C library. For each real-time process, there exists a shadow process in the normal rhythm as a replica of the real-time process. They have a one-to-one thread mapping. The shadow process executes remote system calls in the normal rhythm general-purpose operating system in behalf of the corresponding real-time process. I will explain the details later. It is a user space process like the device emulation of QEMU-KVM, and both processes share the same physical memory with the same memory address space, and illustration of the memory address space is shown in this slide. With the rich real-time process executing, same as typical process, it uses system code to interact with the operating system. We provide the same system call interface as Linux to compile with the API compatibility. System calls are executed in real-time rhythm or normal rhythm, or both, according to their semantics. We categorize the system calls into three types: the real-time system calls, remote system calls, and a dual system call. Real-time system calls are executed in the Swift RTOS kernel, and remote system calls are executed in the general-purpose operating system. Dual system calls are a combination of the real-time and remote system calls. It is carried out in both rhythms to synchronize the process attributes, for example, the memory map of the rich real-time process or the shadow process. I will now explain the real-time and remote system calls. Real-time system calls are used to access real-time devices and facilities in Swift RTOS. For example, threading API and semaphores. These are handled locally as Nuttx system calls and implemented Nuttx for deterministic execution and higher timing accuracy. Although both systems are process-compatible systems, there are some differences between Nuttx and Linux, preventing directly reusing Nuttx system calls for real-time system calls, which are encoded in Linux API. This includes, for example, different kernel data structures. To achieve API compatibility, we added Linux compatibility layer and implemented missing but essential system calls, and also incompatible structures and flags are translated with stubs during the system calls. On the other hand, remote system calls provide access to non-real-time devices, file systems, and features of general-purpose operating systems in the normal rhythm. Remote system calls are dedicated from real-time rhythm to normal rhythm by messages and notified by inter-processor interrupts (IPI). The overall calling procedure is shown as this illustration, having a RT processor and a shadow processor in different rhythms on the same piece of memory and memory address space. First, the thread and RT process issue a system call to the Swift RTOS kernel, and the Swift RTOS kernel marshals the system call number and arguments as a message and notifies the general-purpose operating system with IPI. The general-purpose operating system kernel retrieves the message and forwards it to the thread in the shadow process. Having the arguments, shadow process executes the system call on behalf of the real-time process. Because the two processes have the same memory and memory address space, this will succeed, and after the system call, it marshals the return values and sends it back to the real-time process. Next, into the evaluation of our proposed system, we use the following environments. We use a Linux machine with the software given in the tables, and we test it against 5 different configurations, including the vanilla Linux, PrinRT, our proposed system with vanilla Linux, our proposed system with PrinRT, and Xenomite 3.0. First, we evaluated the timer accuracy of our proposed RTOS. We use cyclic tests to benchmark this. Secondly, tests measure the amount of time between a thread set a timer and the timer expires, and all configuration use the same EOF binary without recompilation. Instead of dynamite, which requires a modified version of secondly test, the parameter was given as following. During the test, the system was loaded with an additional stream benchmark. The result of 100,000 measurements is shown in the graph as violin parts, showing the minimum, maximum, and the distribution. From the top to bottom is Boolean Nuttx, Boolean RT, ZMI3, our proposed RTOS with Boolean Nuttx, and proposed RTOS with Boolean RT. As you can see, the distribution of our RTOS is smaller and well bounded. Our proposed RTOS is the fastest and has the best jitter compared to the existing solutions. Its jitter is about 4 microseconds compared to 40 microseconds of Xenomite and 60 microseconds of Boolean RT. We observe that the compound real-time operating system performance becomes better when using Boolean RT as a general-purpose operating system. In the second experiment, we like to evaluate the interrupt latency and the jitter of our proposed system. We like to measure the latency of a hardware interrupt. The overall setup is in this figure. A serial device was attached to the system. The system was programmed to generate an output after the input is received. A signal generator generates a pulse to the serial device. The original pulse and the pulse generated from the system are measured by an oscilloscope to observe the timing difference. We also run stream as an additional load during this evaluation. The result with 1,000 measurements is shown in the graph as violin parts. From top to bottom is Boolean Nuttx, Boolean RT, our proposed operating system, with Boolean Nuttx and Boolean RT. Our proposed RTOS has the best latency and jitter performance with real-time devices comparing to existing solutions. We can achieve a maximum latency of 10 microseconds with about 2 microseconds jitter, while the others has a maximum latency of 50 microseconds and a jitter of 30 microseconds. Again, we observe that the compound real-time operating system's performance become better when using Boolean RT as a general-purpose operating system. We have also measured our system call handler performance against other environments. We found out that our system call handler is faster than Boolean RT and Xenomite when handling real-time system calls. However, for remote system calls, the latency is large because of the IPI latency. We evaluate our design and implementation's compatibility to a Boolean Nuttx with a paper published in EuroSys 2016. Each linear system call is classified according to their probability in the Debian repository, and in the table we can find that our design is able to support all 224 indispensable system calls, and only some important and low importance system calls are not supported. This proves that our system is compatible with Linux. We also evaluated the compatibility with various X-window applications, including GhostScript, image-related applications, terminal applications, and browsers. Using binary from Ubuntu repository, Vim, Registrio, GhostScript, SRAM with SH, and ImageMagick did work in the real-time rhythm. However, MS, GNU Terminal, gedit, and Firefox didn't. We have also successfully run oscilloscope application for the real-time rhythm with real-time drivers while the window was displayed in the normal rhythm. So about the related works, first is the MC kernel published by Jirofi in 2015 proposed a process-compatible high-performance computing programming environment. It provides a process to access devices via Linux drivers. Our shadow process is similar to the process. However, we apply this to the real-time systems. Another one is FlexSC, published by Solaris in 2010, proposed a synchronous system calls compatible with existing system call interface. We extended this concept to delegate system calls not to the original kernel but to another kernel. We use IPI to communicate between the kernels, and we preserve the real-time property when such delegation happens. In conclusion, we propose a new compound real-time operating system design and achieve a good real-time performance. It provides access to general-purpose operating system's rich features, and it reuses the two transparent formats of common general-purpose operating system. We implement the compound RTOS with Linux, Nuttx, and Jailhouse, and the real-time performance is better than existing solution related to Linux, and it requires no modifications to the general purpose operating system. The overall feature is superior than existing solutions related to Linux. For future work, we would like to explore the possibility of using different combinations of RTOS, general purpose operating system, and hypervisor. For example, substituting the RTOS as driver or free RTOS. Furthermore, this project is being open source and slowly merging back to the upstream Nuttx repository, and here's the current URLs for the research artifacts. And this is my presentation. Thank you for your attention.